Jay? Oh,
I'm sorry, I was just thinking. I was wondering if we could just go through all of them.
okay. Explain how the first derivative of a function determines whether the function is increasing or decreasing.
I think because it shows the slope.
Well, if the function is increasing, the first derivative is positive. If the function is decreasing, the first derivative is negative. That's the answer.
Mm-hmm.
And that's pretty important. In other words, that's a hugely important thing about derivatives and about functions. Always remember that. That's probably the most important thing. Okay? Explain how to apply the first derivative test. Well, let's say I have a function like this. I'm not sure that these are the questions we want to go over, but I'm going to try to go over them very quickly. To me, the only questions worth any value are problems. I know that's a unique point of view, but there's a function. Now, if you took the derivative of that function, you would find 3 zeros. One would be right there. There's a 0 tangent line, 0 slope. Another one would be right there. Another one would be right there.
Yeah.
Which is a relative maximum?
A,
What's the relative minimum?
B,
Which one is neither a relative minimum or maximum?
0.
Yeah, it still has a 0 slope. So in order to determine which of these points are maximums and minimums, I apply the first derivative test. Well, how do you apply it? How do I know that this is not a relative minimum or maximum?
Because it's positive going into this. The slope's positive going into it, and the slope's positive going out of it.
Exactly. And what you need is for them to be different, first of all. And if I apply the first derivative test to that, it's positive going in, coming out negative. That makes it a maximum. To this one here, it's negative going in, positive coming out. That makes it a minimum. So this would be a perfect example to explain what they're looking for in that question. The reason I don't like questions like this is they're subjective. There is no answer you can give that some teacher wouldn't find fault with. And in other words, there's not just one answer. I don't like questions like that. We'll go through these as fast as we can, just so we can get to the real problems. Okay. Number 3, sketch the graph of a function that has neither a local maximum nor a local minimum at a point where f prime equals 0. Another reason these are tough to do is that it's tough to do online because you can't sketch online. This function right here has a derivative that's 0 that is neither a minimum nor a maximum, because the slopes don't change signs. They go plus, 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 plus. In other words, it fails the first derivative test.
Mm-hmm.
Explain how to apply the second derivative test. Now this one only has 2 points on it. That one and that one, where the tangent line is 0. In other words, where the first derivative is 0. How do I apply the second derivative test? What does it mean to apply the second derivative test?
Take the second derivative of the given function.
It has to do whether it's positive or negative at these points. In other words, once I determine that, let's say, x is 2 and x is 4, once I determine that the first derivative is 0 at 2, I have to determine whether it's a local maximum or minimum. How do I do that? Using the second derivative test. If second derivative is less than 0, it's concave down. That's concave down. That means it's a maximum. If the second derivative is greater than 0, it is concave up. That fits, right? Concave down goes with negative, concave up goes with positive. And if something is concave up, it must be a minimum. So that's the second derivative test. Is if it's negative, it's a maximum. If it's positive, it's a minimum. And I'm talking about at these points. In other words, f prime of 2 would be negative, and f prime of 4, f double prime of 4 would be positive in the graph that I've drawn. Okay? If f double prime is equal to 0, you can't tell anything about it, and you have to go back and apply the first derivative test. In other words, the first derivative test would also tell us whether that was a maximum or a minimum, because it goes plus, 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 and comes out minus, minus, minus. That means it's a maximum. If it goes in minus, 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 and comes out plus, 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 that's a minimum. That's the first derivative test. But you will find that the second derivative test is much faster than the first derivative test, as long as it's not equal to 0. If it's equal to 0, you have to go back and apply the first derivative test.
Could you explain again how to do the second derivative test?
Yeah. What you do is you find the points on the curve where the first derivative is 0, which in this case are 2 and 4. And then you take the second derivative and evaluate it at those 2 points. In other words, what that means is the second derivative evaluated when x is 2. This means the second derivative evaluated when x is 4. So just take the derivative of the derivative, and you get your second derivative, and that's a function, and evaluate it at this point, 2. If it's less than 0, it's a local maximum. If it's greater than 0, it's a local minimum.
Okay.
Okay? It's basically as straightforward as that. And it's not hard to memorize, because less than 0 would translate to concave down. You're going to get into this concept of concavity here. You're already in it, I can see. And it's an important concept in calculus. The concavity of a function. Do you have any questions about that at all? Let me draw a few functions. You tell me what concavity is on all of them.
Concave down because the slope's decreasing.
Through the entire domain. Not necessarily because it's the slope's decreasing. Yeah, I suppose it is. No, you're right. In other words, when the slope's decreasing, the first derivative is decreasing. And when the first derivative is decreasing, the second derivative is negative.
Mm-hmm.
And when the second derivative is negative, it's concave down. Sometimes it's not so easy to tell concavity. I'm going to point. What's the concavity starting from the left?
It's concave up.
Until about there, right?
Yeah.
I'm going to mark those points with an X because they have a special name. That's the inflection point. It's where the concavity changes. When you go from concave up to concave down, there's always an inflection point. Has to be. You can't get from up to down without an inflection point. Now, about here, it changes again. That's concave up again. So there's another inflection point right there. And the key here is that inflection points come when the second derivative is equal to 0. So if you want to know where that is on the x-axis, take the second derivative of the function, set it equal to 0, and it will tell you what these 2 points are.
Okay.
Now, this stays concave up all the way to there. That's still concave up until you see it specifically turn around. In other words, if this function went all the way to infinity, that would be concave up from negative infinity to whatever that point is right there. Then it would be concave down from A to B, and then it would be concave up from B to infinity. And there would be exactly 2 inflection points, one there and one there. The inflection point's always where it turns around. It goes from concave up to concave down. And you can always get it by setting the second derivative equal to 0.
Okay.
All right. I hate to spend our entire first session here on these word problems, but each one of them is important in its own way.
And an inflection point is when the slope changes from positive to negative, right? Or
not the slope. No, it's not true. In other words, if I have a first derivative, I'm going to pull up something here that I pulled up before. Hopefully I can find it a little quicker this time. This relationship between concavity and first derivative and second derivative. Right here. Here's the top one is the original function. Okay? Notice the concavity of the original function. All of this is concave. Hold on. That's all concave down, right?
Yeah.
That's all concave up, right?
Just when the concave switches from negative, like down to up.
Somewhere in between there is where it switches. That's the inflection point. And if you look at the second derivative, in other words, this is the first derivative. Well, notice where the bottom of the first derivative is. That's the inflection point. And if I take the first derivative of this, I get a 0. So the second derivative is 0. Here, let me show this. Let me minimize it a little bit more so I can get all three graphs on the same page. There we go. In other words, that inflection point needs to be 0 on the second derivative, and it is right there. And all of your rules apply to this picture. That's why I'm amazingly shocked that I don't see this picture on any calculus book except my stupid calculus book. That's where I got this picture. But I got 3 other calculus books and nowhere does it show these one above the other like this, which is so valuable. Notice that's a cubic function. Notice that's a quadratic function. And notice that's a linear function. As you take derivatives, you reduce the power by 1 degree each time, right?
Mm-hmm.
Multiply by the exponent and subtract 1 from the exponent. So this is a cubic, this is a quadratic, and this is a linear. And all the rules apply. Wherever the original function is increasing, the first derivative is positive. That's positive between those 2 points. Wherever the first derivative is decreasing, second derivative is negative. It's negative right there. So all of your rules about increasing, decreasing, positive and negative apply. And furthermore, concavity applies everywhere. In other words, if I want to treat this as the original function, that's concave up everywhere, right?
Yeah.
Well, its second derivative would be positive everywhere. I'm sorry, I didn't mean to use that as an example. But you can see when it's concave down, right there, if I look at the second derivative, it's negative. The whole place where it's concave down, it's negative. And if I look where it is concave up, the second derivative is positive. Questions?
No?
Okay, let's go on. I don't need to keep this chart up here. I'm going to minimize it in case we need it again. But let's go back and look at these questions. Let me look at 5. I'm going to try to do these quickly. So if the second derivative is positive on that interval, it's got to be concave up.
Mm-hmm.
So let's draw a chart, and we'll call the interval from there to there. It's concave up, right, on that entire interval? Describe the relationship between the graph of f, which is what I have here, and its tangent lines on that interval. Well, there's one tangent line that, well, no, that's not one tangent line. We have a bunch of them. What's going on with the tangent lines? What are they going from? What's their sign here? What's their sign over here?
Negative to positive?
that's always concave up. If it's going positive to negative, it's concave down. So that's the answer to this question number 5. Describe the relationship between its tangent lines on the interval. Well, if it's concave up, which means it's positive, the second derivative is positive, then the tangent lines must go from negative to positive.
Okay.
Next question, I can use exactly the same curve. Well, let's change it a little bit. They said sketch a function that goes from concave up to concave down as x increases. Well, that's concave up, that's concave down as x is going to the right, correct?
Mm-hmm.
Okay. Describe how the second derivative of this function changes. What's the second derivative going to be? Right there.
0.
If the second derivative is positive, it's concave up. If the second derivative is negative, it's concave down.
So it'd be negative.
Is this concave up or down?
No, so it'd be concave up.
Which means the second derivative is
Negative.
positive. Positive goes with up. Negative goes with down. Okay? In other words, that's not the first place in calculus where that's true. Positive velocity is going up. Negative velocity is going down. Same thing with concavity. If concavity is up, second derivative is positive. If concavity is down, second derivative is negative. What's an inflection point? These are things, even though I don't like word questions, I have to say that every single one of these first 10 questions you have to know. This is not something esoteric. This is integral part of calculus. If you want to understand calculus, you got to know this stuff.
Well, it's in between both of the concaves. So it's
where concavity changes.
Yeah.
Got to change. It can't just be between two concavity ups. It's got to be between where it goes from up to down or down to up. That's where an inflection point is, right there. And right here. Notice that is concave down. This is concave up, therefore there must be a point in between that is the inflection point, where the second derivative would be equal to 0. Remember that the first derivative equals 0 is where you have local minimums and maximums. Second derivative equals 0, inflection points. Give a function that does not have an inflection point at a point where f double prime equals 0. Well, let's take a very familiar function. Y equal x squared. What's the second derivative of that?
2x.
That's the first derivative. What's the second derivative?
2.
Is that positive or negative?
positive, so that means it's concave up.
Up, exactly. And this thing is concave up the entire way. There is no inflection point on this. In other words, there is no place where the second derivative is equal to 0. Okay, let's take another function. Common function, the cubic function. Y equal x cubed. What's the first derivative?
3x squared. I mean, no, 3, yeah.
Second derivative?
6x. And then there's a point where it passes through the x-axis, which is at 0.
What's the concavity from that part?
Negative.
Down.
Or down, yeah, sorry.
So the second derivative is negative, right? Well, notice that any x value that you plug in that's negative, which is where my circle is all of those are negative x values, we get a second derivative that is negative. That means it's concave down. And notice that if I plug in any positive x values, I get concave up. So it passes my second derivative test. When the second derivative is positive, I'm concave up. When the second derivative is negative, I'm concave down. And what about when the second derivative is equal to 0? Where does that occur?
I'm a little confused.
Second derivative is 6x.
Yeah.
Where is 6x equal to 0? At what value?
At 0. It's just at the origin.
Okay, it's at x equals 0.
Yeah.
And that's the inflection point. That's where the concavity changes between down to up. So this function actually illustrates everything you really need to know about second derivatives and first derivatives. And which is the concavity matches for, in other words, when I had a parabola, I couldn't take the second derivative of it. It was a constant. But because I started with a cubic function, I was able to take the first derivative and the second derivative and have it be a function of x, so that I can see that whenever x is positive, the second derivative is positive, concave up. Whenever x is negative, the second derivative is negative, that's concave down. And whenever x is 0, the second derivative is 0. That's an inflection point. So this really illustrates everything about first and second derivatives and concavity and inflection points. All right, let's keep going because I want to get to these word problems. Give a function that does not have an inflection point where the second derivative is equal to 0. Well, let me think for a moment. Second derivative is equal to 0 and it's not an inflection point.
Would it be like 5x or something like that? Because then the second derivative would just be 0 because you're taking a derivative of a constant after that.
Yeah. Good answer. In other words, yeah, I should have drawn it a little bit better. In other words, y equal 5x. You're absolutely right. That's a perfect function.
Mm-hmm.
Second derivative is 0 because the first, in other words, if y equal 5x, first derivative is 5, and the second derivative is 0.
Which is a constant.
Yeah, and yet there is no inflection point anywhere here. And in fact, there's no concavity here. Notice that the second derivative is neither positive nor negative. That means there's no concavity.
Does it just mean that it's just a positive slope all the way through, so it's impossible for there to be any? concavity.
Concavity really applies to when you have curvature. When you have a linear function like y = 5x, you don't have any curvature. You have a straight line. It's a constant slope throughout. So concavity comes into play whenever you have any kind of curvature on a line.
What if you have an absolute value function?
No curvature.
No curvature, so there's no concavity to it.
Exactly. That is not concave up. In other words, we have to examine the concavity between that point and that point because it is not differentiable there. The only time it makes sense to talk about concavity is when it's differentiable on the interval. In other words, there's no interval there. That looks like it's concave up, but it isn't really. What you have is no concavity that on this part of the interval, and you have no concavity on that part of the interval, and it's not differentiable at the cusp or the corner, so there's no question about first or second derivatives. For concavity to play, it has to be differentiable over the interval.
Okay.
Number 9. Is it possible for a function to satisfy the original functions greater than 0, the derivatives greater than 0, and the second derivative is less than 0? Explain. Yeah, that's easy. The original function is greater than 0, so I merely have to be above the x-axis. The derivative is greater than 0, which means all I have to do is have positive slopes. There you go. That's nothing but positive slopes. And yet the second derivative is less than 0 because it's concave down throughout the entire interval, which would make the second derivative negative or less than 0. So your square root function would be such a function. In other words, if I just draw the square root function, starts there and goes up like that. Well, that's positive everywhere. Its first derivative is positive everywhere. The slopes never turn negative. And the concavity is negative, which means the second derivative is less than 0 on any interval you want, from there to there, or there to there, or 0 to infinity. All three of those things are true from 0 to infinity of the square root function, which is y = square root of x. All right, number 10. Again, the cubic function. It's a pretty good function to use when you're talking about first derivatives that are 0 that don't represent extrema. So our function is continuous on this interval, agreed?
Yep.
And it does have a critical point right there. Critical point being where the first derivative is 0. Well, the first derivative is 3x squared. It's certainly 0 at x = 0. The slope is 0. And that's the definition of a critical point. And now, if I take the second derivative, I get 6x. Well, the second derivative is equal to 0 also at x = 0. In other words, the second derivative evaluated at 0 is still 0. Tells me there's an inflection point there, possibly. And there is. That's where it goes from concave down to concave up. How do you determine whether f has a local extreme value at x equals 0? In other words, our second derivative test didn't tell us. If the second derivative is neither plus nor minus, it doesn't tell us whether we have an extreme value at that point.
Mm-hmm.
What do we have to go rely on when the second derivative is 0? To determine whether that's a local minimum or maximum. We can see it isn't. But the reason it isn't is because the slopes don't change sign. In other words, if you go back to the first derivative test, the slopes go plus plus, come out plus plus. That means it's not, the slopes have to change sign for it to be a maximum or a minimum. If they do not change sign, as is the case here, then it is neither a local, it's not a local extreme value.
Yeah.
So you need to use the first derivative test here. When the second derivative test gives you 0, now with most every function, the second derivative test is the easiest way to do it. Because the first derivative test, you have to choose points to the left of your point and to the right of your point. You have to figure out what the first derivative is, both sides. It's a lot harder to use the first derivative test than it is the second derivative test, especially if it's a simple polynomial that's easy to differentiate. Like something like this. Okay, that's going to be super easy to differentiate. It's just a simple polynomial that I can use the power rule throughout, all three terms. So, and I'm only going to lose one value of exponent per derivative, so my second derivative is still going to be a quadratic. And I'll be able to tell whether the second derivative is positive or negative or 0. All right, let's get to some of these problems. I think that those were useful, but only to a certain extent. Actually, those were probably 10 of the most useful word problems I've ever seen in math. Normally, I hate word problems. I don't think they teach much. They're subjective. Your answer has to be in proper sentence structure and all kinds of things. Math has got numbers, equations, and one correct answer, in my opinion. However, these 10 questions really did ask 10 very important questions that you need to know. You need to know how first derivative relates to second derivative, relates to inflection points, relates to increasing, decreasing, relates to local maximums, minimums. Every single one of these questions taught you a key thing about functions. And that's what calculus is the manipulation of functions. All right. The only problem with these is it doesn't give you a chance to answer any of them. And I really don't like tutoring sessions where I talk the whole time. I mean, you could be asleep on your end and I wouldn't know it. Not that I know you're not, but tutoring sessions are most effective when you give me answers, not when I teach you or when I give you answers. You know what I'm saying?
Mm-hmm.
And questions 11 through 15 are going to require me to give you answers because they require you to sketch something.
Mm-hmm.
So let's skip those and go straight to 15 to 16. I want to do some things where you have to answer, not me. Following figures give the graph of a derivative of a continuous function that passes through the origin. So we're looking at the derivative graph here, not the original graph, the derivative graph. Tell me what degree polynomial the original graph is on 15.
2.
No, the first derivative is 2.
Oh, no, that'd be cubic then.
Yeah, exactly. Both of these, 15 and 16. The original graph is a cubic. You lose exactly 1 power as you take derivatives.
I guess you have to sketch for this one too, though.
Yeah, all right. Let's go on. Seriously, I mean, I don't mind doing it. I could do it, but I don't think it's as valuable for you as you doing stuff. So let's look at 17. I mean, we only have 15 minutes here. So find the intervals, and these are not that easy either. Find the intervals of which f is increasing and decreasing. How do we do that on 17?
Take the first derivative.
Okay, I was just about to say that if you don't know the first step on a calculus problem, guess and take the first derivative. That is almost always the first step, believe it or not. What is the first derivative?
Negative 2x.
Okay. Now, how do we tell where the original function, this one, is increasing and where is it decreasing?
We set it equal to 0.
No, it's increasing when this is greater than 0. So minus 2x has to be greater than 0. Solve that inequality.
It would just be x equals 0, is greater than 0.
If I divide both sides by minus 2, I got to switch the direction of the inequality. There's your answer to that. In other words, the first derivative is positive whenever x is negative, correct? That's where the original function is increasing. And if I were to graph this original function, looks like this. It's quadratic, opening down. You can see that it's increasing wherever x is negative. When is it decreasing? Whenever minus 2x is less than 0. Well, solve that, divide both sides, switch the direction because you're dividing by a negative number, and you get that whenever x is greater than 0, the function is decreasing because the first derivative is negative. That's what that means. The first derivative is negative. Okay. Now, it says superimpose the graphs of f and f prime to verify your work. Well, that's pretty easily. That's an easy enough graph of the original function. That's not hard to do. Well, and that's not hard to do. Minus 2x is a slope of 2, and it's negative, and it goes through the origin. So there's the equation of the first derivative. That's f prime of x. That's f of x. And if you look at it precisely, we can tell that when f of x is increasing, the first derivative is in positive territory. When f of x is decreasing, the first derivative is in negative territory. Okay. Yeah, we got time to do 18 also. Now, let's draw the graph on 18 first. This is opening up and going through negative 16. In other words, it's got a vertical shift of negative 16, down 16. Okay? So there's that graph there. That's f of x equals x squared minus 16. Well, what's f prime of x?
2x.
If I graph 2x, goes through the origin, it's got a steep slope, it's positive slope. There's the two graphs superimposed on one another. Now, where is the original graph increasing? What interval? Black graph.
0 to positive infinity.
Where is it decreasing?
0 to negative infinity.
Notice that agrees with where f prime of x is less than 0 when x is negative. F prime of x is greater than 0 when x is positive. Just because of this. There's f prime of x. So we know where it's positive and where it's negative. And it agrees with where the original function is increasing or decreasing. Same directions? I think so. Where it's increasing, where it's decreasing, and superimpose the derivative on the function. What's this 19? What's the function look like?
Does it have a horizontal shift to the right?
What is the name of the shape of the curve?
It's a parabola still.
Okay. And it opens up, and you're absolutely right. The vertex shifts one to the right. Oops. Like that. Okay. Now, take the derivative of that. What is f prime of x equal to?
It would be 2 times x minus 1 in parentheses times x.
No, just x times the derivative of the inside. What's the derivative of the inside?
Which is nothing. So it would just be 1.
It's not nothing. If it was nothing, it would be a lot different. Nothing is not the same as 1. Nothing is 0.
I was just saying like it was just irrelevant.
I know. But the reason I corrected you is because there is a big difference between nothing and 1, or nothing and 0. Okay? So that's the derivative. And if I multiply that out, I get 2x minus 2. So I know where to draw the derivative function. I start at minus 2, positive slope, steep slope, steeper than 1. Okay. And draw it quite right here. I drew the derivative function right. I just didn't put the original function in the right place. The reason I know is that the original function, the vertex has to be right there, right?
Mm-hmm.
In other words, I know the original function is x minus 1 squared, so it's a parabola that opens up whose vertex has been shifted 1 to the right. So that's where the original function has to be. That must be the point 1. And our derivative function, the only reason I know that this is now correct is because our derivative function is 0 right there, right?
Mm-hmm.
In other words, it should be. Well, if I plug in 1 for x, the derivative function is 0. So the slope when x is equal to 1 is 0, which both of the black and the pink curves show. The slope of the pink curve is 0 at 1, and the value of the black curve is 0 at 1. The original curve is increasing on what interval?
2.
What interval?
Oh, 1. No.
An interval is between 2 points.
I don't know what it was. Sorry, I wasn't really thinking there. It was 1 to infinity.
Okay, good. Where is it decreasing?
Negative infinity to 1.
Yeah. The only question about these kind of questions is, do you define it in terms of the x-axis or the y-axis? And oddly enough, you define it in terms of the x-axis always. Whenever you're listing interval notation, it is in terms of the x-axis, not the y-axis. Okay? So when I say negative infinity, I mean that way. When I say positive infinity, I mean that way. I don't mean negative infinity up there or positive infinity up there.
Mm-hmm.
All right. Let's take the second one. Give me the first derivative of this, number 20. Now, oddly enough, I don't know how to graph that. It's not that easy to graph. What's the first derivative, first of all?
It'd be 3x squared plus 4.
Well, oddly enough, I do know how to graph that. That's a parabola, right?
Yeah.
Where's the vertex?
At the origin, it's at 0, 4.
Right.
For the point.
And it opens up and it's skinny.
Yeah.
So that's the graph of that function. But that was the first derivative. Now let's see if we can go back and figure out what the function, how to graph the function. Well, is the function increasing or decreasing?
Both?
No. First derivative is what? Positive or negative?
Oh, so it would have to be increasing.
Have to be increasing the entire domain.
Yeah.
We know that the first function is a cubic. It's just not a cubic like x cubed, which goes through the origin on that key point. So what this must do is something like this. In other words, instead of going through the origin, it goes like that. Now, you can see that the original function is increasing the entire way. So that agrees with the first derivative. The only thing that doesn't really agree is the fact that the first derivative is never equal to 0, right? The pink graph is never equal to 0. See that?
Mm-hmm.
That means the original function can't have any flat tangent lines. So this can't be right. Can't have flat tangent lines. I know that it's increasing the entire way, but it doesn't necessarily have to have any flat tangent lines. What if I draw it like this? There. Now it's got no places on the original function where the first derivative would be 0. And that agrees with the original. In other words, the pink curve so far agrees with the black curve. There's no flat tangent lines. In fact, the tangent lines go plus, 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 plus. Therefore, the first derivative should be in positive territory the entire way.
Okay.
Now, if the black is the original function, it's concave down there. It's concave up there.
Mm-hmm.
That means that the original function, the second derivative would be negative where my arrow goes down. It would be positive where my arrow goes up. Well, let's figure out what the second derivative is. 6x. Perfect. It's positive everywhere. When x, when x is negative, it's down. When x is positive, it's up. So the curve that I have drawn fits everything. And this is a very common thing in calculus where they give you the first derivative and you have to construct what the original function looks like. And it's not that easy. You have to use all of these rules. In other words, if you know the first derivative is positive everywhere, which it is here, then you know the original function is increasing everywhere. If you know the first derivative does not have any zeros, then you know the original function has no flat horizontal tangent lines. If you know, remember this pink is the first derivative. So if the first derivative is decreasing, that means the second derivative has to be negative, which would make it concave down.
Mm-hmm.
And when the first derivative is increasing, the second derivative would have to be positive, which would make it concave up. So the black line that I drew, I believe, is the answer to number 20. That is a function that would work in terms of its derivative, the function, where it's increasing, where it's decreasing, where its concavity is, up, where it's down, where its flat horizontal tangent lines are, all of the key things. And everything I just mentioned are the key things for these things. In other words, everything that was talked about here, increasing, decreasing, first derivative test, local maxes, local minimums, second derivative test, these questions actually cover all of your very key things about functions, first derivatives, and second derivatives. Much to my surprise. I'm glad we reviewed them because these are 10 very good questions for teaching you about the relationship between functions, their first derivatives, and their second derivatives.
Yeah, I agree.
Jake, I'm going to let you go. What is this, Tuesday? I will talk to you Thursday and we can finish up some of these. I noticed they get a lot harder. Well, actually they get harder not until, these are all polynomials. These aren't going to be hard. But once you get to 25, now we're talking complex, more complex functions. Both 25 and 26 are both fairly complicated to draw the function and to take the derivative. We'll get to that on Thursday.
All right.
Talk to you then.
See you.